working with radicals, a couple things that we're doing. Converting between mixed and entire radicals. We're going to compare and order them, and then we're going to identify any restrictions that would make your radical unsolvable, or rather would make it an imaginary number. So just some background information we have for when we're working with radicals. This is your radical sign, your root symbol. The little number above your root symbol is what we call the index. That's to what root you're taking the number to, and that number has a special name called a radicand. So just for example, if you were looking for the third root of 8, 3 would be the index, and you're looking for 3 values, that would give you this, and 8 is the radicand. We typically don't write the index if it is a square root. So if this is to the second root, we'll just leave it as a 2. So we won't write the 2. If it's anything above a 2, we need to write to what root we are taking the radicand to. In the TI-83, if you need to use a third root or even in a higher root, you press the math button on the TI calculators, and it'll bring up this menu, and this is what you'll use for a third root. And if you need to use a higher root, you need to put in the number first when you're putting in this function. So if you're doing the 5th root of, say, 32, you would type 5 first, and then you press math and open up this function. You click it, you press OK on this one, and then you'll put in the number that the radicand, what you're trying to put to the 5th root. So restrictions. Underneath a radical, there are certain numbers that will make it unsolvable, that it would be impossible to come up with 2 exact same numbers that would make it solvable. So in the case of variables underneath the root symbol, those variables have to be restricted in particular ways. And we're going to talk about those. If this value of x happens to make this statement less than 1, the equation, the expression, becomes unsolvable. So for example, let's say I had an x of 2. Then if I took 4 minus x and change that into 4 minus 2, now I have the square root of 2. Now that's a solvable number. You can end up with a non-repeating, non-terminating decimal, a rational number that is a real number, but there's it's a valid number to work with. If I had an x that was equal to 4, now we're getting a little bit closer to the danger zone. So the square root of 4 minus x, if I replace the x with 4, this becomes 4 minus 4, and that is root 0. Now 2 numbers that give you 0, that's still a valid number. 2 numbers to multiply together to give you 0, 2 equal numbers is 0 times 0. So that one's still okay, just like this one. But notice how as we get higher, we're getting closer to negative numbers. Let's try an x equals 5. If my number gets too high, then if my x gets too high, then when I do the substitution, so replace my x with 5, now I have a number that would be invalid, square root of negative 1. There's no 2 numbers, no 2 exact same numbers that you can multiply to get you a negative value. this becomes an imaginary number. So let's even look at one that would be typically a perfect square of a value underneath that would be a perfect square. Let's replace x with 8. That one's no good. So let's try x equals 8. So square root of 4 minus x equals root 4 minus 8. And then this equals root negative 4. Now there's no two equal numbers that would give us negative 4. I know the first inclination is think, well, 2 and 2. But they wouldn't be two equal numbers because it would be positive 2 and negative 2 that would possibly get us negative 4. And those are not equal numbers. They're opposite numbers. Opposite is not equal. So this is no good either. So we need some way of defining what are permissible values to have in our radical for our variables. We need to define what x can be and what x cannot be. So how do we do that? We have a look at the radical, and we are going to find out what would make x plus 1 less than 0. We want to find out what would make x plus 1 less than 0. So we're going to manipulate this inequality algebraically. We want to solve for x, and we'll find out what value for x would make x plus 1 less than 0. So bring the 1 over to the other side by subtracting 1 from both sides, and you'll find that if x is less than negative 1, think about any value for x that's less than negative 1, that would end up giving us a negative value for our radical, and it would become an imaginary number. So any value for x that's less than 1 is no good. For j, just what's underneath the radical there, we want to find out what would make that less than 0. Well, there's no manipulation needed here. Just any j term that's less than 0 would make this value for j impossible. Would make it an imaginary number. I don't want to say impossible. What about the third root? Now this is a little bit different. What value for y would make this impossible? So for third roots, this is a little bit different because we're not worried about those negative terms because there can be 3 exact same terms that give you a negative value. So for example, let's just use a nice simple example. The third root of negative 8. That looks unsolvable, but it absolutely is. So the third root of negative 8, we're looking for 3 exact same things that can multiply together to give us negative 8. That would be negative 2 times negative 2 times negative 2. So negative 2 times negative 2 times negative 2. Those 3 exact same terms, a negative times a negative is positive, positive times negative is a negative. So this is solvable. Third roots are solvable. Square roots are not solvable. You would run into the exact same problem with fourth roots that you have with square roots. There are no 4 numbers that can multiply together to give you a negative term. With fifth roots, we have the similar setup as third roots. There are 5 exact same numbers that you can multiply together that will give you a negative term. So there's a bit of a pattern here. If your index is an even number, you cannot have negative numbers in that radical. If your index is an odd number, you can have negative numbers. So anything is good for y. Y can be any value. The next skill we're going to look at is expressing radicals as mixed radicals in simplest form. So we're going to be looking at any potential perfect squares that can come out of this number. A nice easy starter route for this is to do a factor tree with your value. So 5 times 10, I'll show you why. 10 can be split into 2 times 5. So root 50 can be rewritten as root 2 times 5 times 5. And that 5 times 5 is our key to simplifying this radical. Any pairs, at least for a square root, any pairs can be separated. So we can separate this radical into two radicals and they would remain true. So root 2 times root 5 times 5. We do know that root 5 times 5 is 25, but that's actually a perfect square. That 25 can be simplified to a whole number. So this becomes root 2 times 5. We'll rearrange that to the proper format. You put the 5 as a coefficient. Now what you really want to start thinking of these as, treat them so similarly as like if this was 5x. This is a term that we know it's an exact term, root 2, but we can start treating this as if it were like a 5x. In terms of the algebra, it works out the same to manipulate this as if this were 5x. Come back to that more later. So this negative 2 on the outside, that's just going to become some multiplier that you can pull out after. Let's have a look at the 80 and see what the biggest value we can pull out of there is. So let's factor tree it. It's a nice, easy skill. 80, I would split that into 8 and 10 to start. 8 can split into 4 and 2. 10 can split into 5 and 2. And 4 can split into 2 and 2. So let's rewrite this in its fully factored form. Eventually you'll start picking up on perfect squares that make up this number. If you're clever with your perfect squares, you might, with your multiplication, you might notice that this is 16 times 5. To get 80, 16 is a perfect square. But in every case, you can easily pull them apart using a factor tree and have a look at what you have underneath. Have a peek under the hood and see if there's any perfect squares there. So you're looking for any pair. So that does work for multiple factors as well. 2 times 2 is 4. This is a 4 times 4 here. So why don't we change that into the 4 times 4. Doing a little bit of extra steps here, but trying to show the whole process. Now we can take this 4 times 4, this perfect square, and we can separate it from the 5 and turn it into root 4 times 4 times root 5. This 4 times 4, we know that's going to be 16. The square root of 16 is just 4. So negative 2 times 4 times root 5. This negative 2 and the 4, we can combine those. That'll become negative 8 root 5. That is simplest form, and that's a mixed radical. Now for the 54, we're going to employ the same strategy, but instead of looking for pairs, we're looking for triplets. We're looking for 3 things that are the same. Again, having a look at 54, if you're good with your multiples, you'll recognize that 54 is, I had one. I'm not sure now. let's just split it apart. So 54, let's split that into 2. There it is. I see it now. 54 split into 2 would be 27. 27 can be split into 9 times 3. 9 can be split into 3 times 3. So this is 54. The prime factors for 54 are 2 times 3 times 3 times 3. So we're looking for a triplet, and we can see our triplet here. So the third root of 54 we're going to change into 2 times 3 times 3 times 3. We do have a triple here, so we're going to separate these two third roots into third root 2 times the third root of 3 times 3 times 3. So 27 is a perfect cube. 3 times 3 times 3 is 27. The perfect cube of 27 is 3. So this turns into the third root of 2 times 3. And we'll combine them together just like we did over here, writing the coefficient first. So 3 times the third root of 2 is our final answer. Moving on. So if we wanted to split these apart, we can look for perfect cubes within it. So if we were to do a factor tree for x to the 7th, it would be 7x's multiplied together. So let's split this. Let's use some of our power laws, and x to the 7 can be rewritten as x to the power of 4 times x to the power of 3. Now x to the power of 4 is going to fit nicely with our fourth root. So this can be solved down to, we can split this into the fourth root of x to the 4th times the fourth root of x to the 3rd, and the fourth root of x to the 4th would just be x. And then times by the fourth root of x to the cube is still in there, and there's nothing more we can do with that. So over here, we're looking for square roots on this one. And so let's pull apart the 63. 63, we know 63 is a multiple of 9, which is a perfect square. So let's split 63 into 9 times 7. The 9 can split into 3 and 3. And there is our factor tree for 63. So let's split that 63 apart, and we're looking for square roots, so if we're looking for pairs, so we're going to do the same thing with these here. So the 63, we're going to change to 3 times 3. We're going to do it all in one big go. X to the 7th, we can split into squares that we can pull out as well. So times x squared times x squared times x squared times x, just x. That's our 7 x's. 3 of them are perfect squares. And then we got to do a little bit more. X to the 4th, we can, that is itself a perfect square, but let's split it apart anyway. So y squared and y squared. So we've got some perfect squares to pull out of here. So we're going to separate this into all of our perfect squares, and then the ones that we can't, we'll leave in one radical. So 3 times 3, we're going to pull that out. We can pull out 3 units of x squared. And we can pull out the 2 y squareds. Sorry, root y squared. And then what we're left with in here, we couldn't pull out the 7 and we couldn't pull out this x. So what we're left with, that will be, what's left as our radical is sorry, 3 is 7x. It's a sloppy 7, but alright, so root 3 times 3 is 3. The square root of 9 is 3. The square root of x squared is x. Square root of x squared is x. Square root of x squared is x. And then y and y. And then nothing to do with the 7x as a radical. Let's combine our like terms, and we'll have 3x cubed y squared times 7x, or root 7x. Alrighty, so let's go the opposite way. If we want to take mixed radicals as well and turn them into entire radicals. So we want to find out what we can do with these numbers on the outside to turn them into the same kind of radical that's on the inside. So in order to turn 4 into a root, we need to square it. And then by squaring it, we can turn it into the root that will allow us to combine them. So we want to write them as entire radicals. So this 4, we want 4 can be rewritten as the square root of 4 squared. They have the same value. But if we have 2 square roots, kind of the opposite here, where we were taking numbers out and then turning them into coefficients, we can take those coefficients and put them right back in. See what we do with this 3 here? We took the pair of 3's out and we turned it into a whole number coefficient on the outside. We're doing the reverse here. If we wanted to turn that 3 and put it back underneath the radical, well, we square it and put it under a square root. So we're going to do that here. We want to take this 4 and put it under the root, so we square it and put it under a root sign. So this will turn into the square root of 4 squared times the square root of 5, and that equals root 16 times root 5. And when you have 2 roots like that, you can put them under one root and have it as 16 times 5, and that's equal to root 80. So do the same with this, even if it's a variable. So we can do square root of negative 9 squared, and we can do this times the square root of n squared times square root of 2. And so negative 9 times negative 9 is 81, positive 81. And n squared is just n squared. And then times root 2. Now we can put it all under one big root and have 81 times 2, which is 162. And then times n squared. For the third root, we do the same thing. We're just going to need to cube it. So to put 3 under a cube root, we are going to cube the 3. It's a lot of 3's. And we're going to cube the x. And then we've got, doing that backwards. Then we've got our 4x still. So the cube, we can 3 times 3 times 3 is 27. So cube root of 27 times the cube root of x cubed times the cube root of 4x. Let's put it under one big cube root. And 27 times 4, 20 times 4 is 80. 7 times 4 is 28. So that's 108. And then we have x cubed times x, which will be x to the 4th. That'll do for now. We'll do some more work soon.